Because pointer arithmetic is kind of a difficult concept to understand and grasp, I wanted to go through one last example that really demonstrates this concept. It does a good job, and if you understand this example, you're going to have no problem with pointer arithmetic. So the first example that I want to show you is the effect of adding an integer value to a pointer. So when we do pointer arithmetic with addition, we can actually see how it works in terms of the addresses. So here in this program, all I'm doing is creating a string, a character array. It's called a string. And then I'm creating a character pointer called p. I'm going through the entire length of the string, which is multiple. So I'm going through the entire array. Just basic for loops, string length of multiple, size of multiple. And then I'm printing out each actual string or character inside that array. And also while I'm doing that, I'm displaying the address and then the address with the actual number, the I, added to it. So let's look at just the output of this, because the output demonstrates a really good example of pointer arithmetic. So let's go to code blocks and run this. So here we are in code blocks. I cleaned up the code a little bit. I used stir length instead of string length because it's an extra include. And I want to just run this. So when I run this, what you'll notice is it's showing you what memory looks like. And it's showing you the values doing the pointer arithmetic. So if you say multiple sub 0, remember multiple just contains a string. But if we look at this and we say look at the array contents, multiple sub 0 is a, multiple sub 1 is a space, and then the rest are string. That's the array. Right next to this is the same as adding 0 to the pointer and dereferencing it, adding 1 and adding 2. And it shows you how you can do pointer arithmetic by dereferencing the pointer itself and adding numbers to it. So the pointer plus 7, dereferencing that, you get G. Then in the third column, I'm showing you the actual addresses as we increment. So the addresses of each element in the array, using the ampersand just on the character array, we see the addresses 060, FE, FF for element 0 and so forth. And then we look at the addresses if we just add to the pointer itself without dereferencing it. And you'll see the addresses line up. And so then we can look at the syntax to see what's going on here in terms of the first thing that we actually display is the index in the array, which is just a counter. And then we display a %C, which is the character at the array. The next thing we're displaying is dereferencing the pointer plus I. So here what we're doing is we're displaying I, and then we're displaying the dereference of pointer plus I, the actual value. So we display as the D, just the actual counter, and then point C is our dereferencing. So P is our pointer, right? P is our pointer. We're just saying P plus I, pointer arithmetic, and then we're dereferencing it. And then to get the addresses, all we need to do to get the array address is say ampersand multiple and then the index. To get the first get the address of the pointer, right here we just say P plus I. To get the actual counter, which is showing you how we're incrementing that P, we just do a P plus %D. But it does a good job of demonstrating the various ways that the memory that we're pointing to, the addresses, are actually displayed and how they're equivalent to the different indexes in an array and the actual pointers. I thought this did a good job. I want to look at one more example that does another good job concerning pointer arithmetic with longs. Because here, these are integers, so all we have to do is add 1 and it automatically goes up to the next byte and so forth. Let's look at what we do. We do longs. So in this example, I wanted to also just demonstrate how you can do the same thing with a long and a long pointer. With the character pointer, it was just a string character array. But even for long arrays, which are different sizes, we can still iterate through them using a pointer, and you can see how the number of bytes actually changes. So even though we say we have a long pointer and we add 1 to it, we're actually adding 4 bytes to it because a long is a little bit bigger. And we'll see that in this example. So now let's run this example in code blocks. So here's our example. Again, we have an integer counter, a loop counter. We have a long array, 15L. We're specifying L. By putting the suffix on there, we specify their L's, their longs. We have a long pointer that's pointing to multiple. Again, because it's an array, we don't have to use the address of operator. We're going to go through the entire long. Here we can't use stir length, we have to use size of. And we actually have to divide it by each spot in the array. So the total size divided by the single spot in the array. That's when we want to jump out, because these, remember, are addresses that are incrementing by 4 bytes each. And again, what we're doing here is we're just displaying both the pointer versus the array and showing you how they're related. And then we're displaying the actual total number of bytes that the long is on our system. And so this again just demonstrates how arrays are related to pointers. So if we run this, we're going to see similar output, but what's a little different here is the address size going up by 4 bytes. So we're going to print out the address and the pointer. So for the address and the pointer plus 0, that's going to be equal to the array sub 0, which is address 6356728. And to dereference the pointer, we'll get the value 15. So p plus 0 is still going to be equal to the array sub 0. And then again, we do the same for p plus 1, p plus 2, and p plus 3, all equivalent to the correct spots in the array for the index. The addresses are going up by 4 bytes, but we can still just add 1, 2, and 3, and we see that the values are the same. And then it tells us this long occupies 4 bytes, and that's why the addresses are going up by 4. But what's significant here is we can still add 1 to it, and the compiler knows to go to the next address. So if whether we have a long or a character or whatever that particular data type is inside of the system, adding 1 or 2 is going to add the correct number of bytes. So just another cool example I wanted to show you